So the plan today is to tell you guys a little bit about some research, some modern trend in tropical geometry, more towards the algebraic side of tropical geometry, and in particular this thing I've been very involved in, which is tropical ideals. And I'm going to try to, the plan for the week is to give you an overview of what tropical ideals are, how do we expect them to help in tropical geometry, what we have done so far, and lots of open questions we have about them. So maybe let me just get started. Let's start with just thinking about what we have seen about tropical geometry so far. Well, the way we've been thinking about tropical geometry so far is that it's a way of combinatorializing algebraic geometry. So if you take a classical algebraic variety like this one on the left, you can tropicalize it, and we learned how to do that the first week, and you will end up with a polyhedral complex that looks like this one on the right. And a lot of properties are preserved when you do these operations. For example, dimension, importantly, is preserved when you do this. The genus of the curve is generically preserved. So the hope is that, or the idea is that we can attack classical problems in the tropical world. We can use this combinatorialization process to attack problems in the classical world by combinatorializing them. So let me just to set the notation again, let me remind you guys what the setup is. The tropical semiring, I'm going to be denoted by R bar, and as I said, it's just the real numbers together with one more element, infinity, and the two operations, tropical addition and tropical multiplication, which for me are going to be minimum as tropical addition, and plus is tropical multiplication. So remember, the tropical numbers are an idempotent semifield, meaning that they're almost a field, and the only axiom of a field that fails is the existence of additive inverses. Okay, so infinity is going to be the additive identity. Infinity, the minimum between infinity and any number a is equal to a. 0 is going to be the multiplicative identity. 0 times a is equal to a. It's idempotent, importantly. So a plus a is always equal to a. The addition is idempotent. And there is no subtraction, and that's what makes algebra hard. That's what's going to make algebra hard. So you cannot solve equations like 2 plus x equals 5. That has no solution. 5 minus 2 doesn't make sense tropically. So it's an idempotent semifield, and there are no additive inverses. And this week we're going to be thinking a lot about tropical polynomials. So, well, I'm going to be denoting the semiring of tropical polynomials by R bar together with the variables x1 up to xn. So these are going to be polynomials, tropical polynomials on the variables x1 up to xn. What's a tropical polynomial on those variables? Is just a polynomial, so a combination, a tropical addition of monomials, and the monomials are just tropical monomials where the multiplication is tropical multiplication. So for example, x squared plus 0 is a tropical polynomial, and x squared you should interpret as x tropical times x, plus is tropical plus, 0 is, having this term here matters because remember 0 is not the additive identity, it's the multiplicative identity. So x squared plus 0 is different from x squared. And here's another tropical polynomial, x squared plus 1x plus 0. 1x, remember, is different from just x because 1 is not the multiplicative identity. These two tropical polynomials are different, right? They have different, for us, we're going to want to think of them as different tropical polynomials because this one has one monomial that this one doesn't have. 1x is a monomial on the right and it's not on the left. Even though as functions, they are the same function. So this is just a warning that we should be thinking of polynomials like really as tropical polynomials and not as piecewise linear functions, I guess. So if you thought of these as functions, you would get the same function, but for us, they're going to be different. They're going to be different elements of this semi-ring of tropical polynomials. So this is a semi-ring, by the way, because you can add tropical polynomials, you can tropically add them, you can tropically multiply polynomials, and it satisfies all the operations of a semi-ring, all the properties of a semi-ring. Okay? And let me remind you guys how to tropicalize varieties, and maybe say it in this way that I have here, because this is gonna guide us later. So suppose you want to tropicalize a variety V, and V is giving us the zero set or the zero locus of some classical ideal, some ideal in a polynomial ring over a field, K. Yeah, so K, if you want to tropicalize, you start with K being a valued field, a field together with a non-Archimedean valuation to the tropical numbers. And remember how we tropicalize the variety is just, well, for any polynomial in your ideal, you tropicalize the polynomial by just substituting the operations for tropical operations. Whenever you see a plus, you change it by tropical plus. Whenever you see a times, you change it for tropical times. And the coefficients, they originally live in your field K, but you tropicalize them to their valuation. You change them by the valuation. And in that way, you end up with a tropical polynomial that has coefficients in the tropical numbers, and now the operations are tropical operations. So that's how you tropicalize one polynomial. But you can tropicalize the whole ideal J of polynomials that defines your variety. What you do is, let's define that as the tropicalization of J. You take all the tropicalizations of all the polynomials in your ideal J, and now, so this is a collection of a lot of tropical polynomials, and you take the ideal that they generate in this polynomial semiring. So you close this collection of polynomials under addition and under multiplication by external polynomials. In that way, you get an ideal here by external tropical polynomials. You get an ideal in the tropical semiring. That's going to be the tropicalization of your ideal. And then the tropicalization of the variety is, you want to say that is the locus where all these tropical polynomials vanish. And for us, that's going to mean, well, the collection of all points in n-dimensional tropical space, such that for each polynomial in this tropicalization of J, the minimum is attained twice.
Do you remember this means to complete the ideal if the evaluation is not objective?
That's a very good question. So actually in the exercises tomorrow, we're gonna see that if you impose some very mild conditions in this field K, you don't need to actually take the set generated, the ideal generated by this, but just the collection of tropical polynomials is enough. Yeah, great. So, but in principle, yes, if you just have the hypothesis that I have here, you do need to close under ideal to create this tropicalization of J, to get an ideal here. And then, yeah, as I was saying, the valuation, the tropicalization of the variety is just the collection of points where for each tropical polynomial in your tropicalized J, in tropicalization of J, you require the condition that the minimum in all the monomials that you see is attained twice. That there are, for each of these polynomials, there are at least two monomials that attain the minimum when evaluated at this point. Okay, so this is what we saw the first week of these lectures. Let's make a concrete example here. Let's have a concrete example here so that we see in like hands-on what's happening. Let's just take J, this classical ideal, very simple ideal. It's a linear ideal generated by one linear polynomial, 2x minus y plus 1. So I'm thinking that this is an ideal that lives in the polynomial ring with coefficients in some field K. Let's say it's trivially valued, so all the valuation sends every element to 0, except for 0 that goes to infinity. And it's generated by one linear polynomial. The variety that this describes, the zero set, the zero locus of J, is where all these polynomials vanish. And because it's principal, well, it's generated by just this polynomial, then that's just saying the zero locus is the place where y is equal to 2x plus 1, just a line in two-dimensional space. So how would we tropicalize this line using this procedure that I described here? What you do is you start with your classical ideal J, which consists of infinitely many polynomials, all the multiples of 2x minus y plus 1. So for example, yeah, here is the generator. Here I wrote down the x times that generator. Here I wrote down y times that generator, or yeah, y times that generator. And here I wrote down another multiple of this one, which is, I believe, the x times the generator minus y times the generator, so that, or yeah, 2 times this one minus that one, or plus that one, so that the xy term cancels in here, and you get this polynomial. That's another multiple of 2x minus y plus, and so on. And you have infinitely many, all the possible multiples of that.
So what's the valuation of 2?
Let's say 0 for this, in this case. Let's say k is trivially valued, so all the elements are going to be sent to 0. Yes, but it does depend on the valuation you choose. But for this example I'm doing, I'm going to say that everything goes to 0. By the way, I realize I'm not looking at the chat. Let me see if I can just to, yeah.
You don't have to look at the chat.
I'll just open it here just to, great, thanks. So you take your classical ideal, which is J here on the left, and you tropicalize all the polynomials that you see there. So for example, the generator tropicalizes to x plus y plus 0, because the valuation of 2 is 0, the valuation of minus 1 is 0, and the valuation of 1 is 0. You get this one. This x times the generator tropicalizes to x squared plus xy plus x. Y times the generator tropicalizes to xy plus y squared plus y. This one here, the last one I wrote down here, tropicalizes to x squared plus y squared plus x plus y, and so on. So here you get an infinite list of polynomials. You close it under addition and multiplication by external polynomials, so you actually get an ideal in the tropical polynomial semiring. And then you require the condition that for all these polynomials in that tropical ideal, the minimum should be attained twice. And because all these polynomials that we have here are just multiples of the original one, in this case, the only condition, well, that's the minimum attained twice condition is just, it follows from just requiring it for this tropicalization of the generator. So you require that the minimum between x, y, and 0 is attained twice, and that's the tropical line that we have seen already. So it's this polyhedral complex with 3 rays there. So let me ask you guys, just as a warm-up question here. Well, the ideal J that we started with is principal. It was generated by one polynomial, 2x minus y plus 1. We tropicalized it. We got this collection of tropical polynomials. Do you guys think that this tropical ideal is also principal? Does it consist of the multiples of a single polynomial, or do we need more than one polynomial to generate this tropicalization? I'll leave you guys 20 seconds to think about. So the question is, the classical ideal we started with is principal. It's generated by one polynomial. Is that also the case for the tropical ideal? Is it the case that this tropicalization of J is the ideal generated by just one tropical polynomial? It's not obvious, but so we can start seeing what, this is a good question to see what kind of tricky things can happen. Yeah, so I see that you guys are saying it's principal, it's not principal. Yeah, it's not so easy to see, but the answer is that it's not principal actually. Even so, it is true that the variety is defined by the tropical vanishing of just one polynomial, this one, x plus y plus 0. But it is not true that all the polynomials that you have here in the tropicalization of J are multiples of just this single polynomial. That was the case classically, but it's not the case tropically. And well, we can see that already here. The second polynomial here is in fact x times this one. The third one is y times the first one. But this fourth one that we have here is not a multiple of x plus y plus 0. You cannot multiply x plus y plus 0 by any tropical polynomial and get this one here. The reason you could do that classically, that you could get this long polynomial as a multiple of this one, is because there was a way of making a combination between these two that canceled the xy term. So here you see that there is no xy term appearing. It disappeared. And that's because we chose some coefficients like 2 times this one plus that one that made exactly this xy term disappear. But classically, but tropically, there is no minus. There is no cancellation. So there is no combination that you can make of this polynomial and this polynomial that makes the xy monomial disappear. Any multiple of xy, of x plus y plus 0 of degree 2 is going to have the xy term appearing, and you cannot get rid of that xy term. So it becomes tricky. The tropical ideal might be, in that sense, is more complicated than the classical ideal. This one was all multiples of this polynomial. This one here, you require more than one generator. And in fact, you need infinitely many generators.
Felipe, is this also the case if we change the valuation?
Yes, good question. It is also the case if you change the valuation. The main problem is that there is no cancellation in tropical algebra. You cannot make terms disappear. And because you can do that classically, then your tropicalized ideal is always going to have polynomials that would require some cancellation, and you cannot do that classically, so you need to add them as new generators. Yeah. Okay, so yes. Any more questions about this example? I think this already shows what can happen when we think of these tropical ideals in the polynomials. Okay, let me continue. So the plan for this week is to tell you guys a bit about algebraic foundations for tropical.
Before we continue, is
yes.
trop J the ideal of all tropical polynomials that vanish on the red thing? I think it does.
That's a very good question, and it's not the case. So it's also not the case classically, right? So you could start with an ideal here that is not radical, a classical ideal that is not radical, and then there will be more polynomials that vanish on the zero locus of J than the ones that are in J. That can happen here tropically, and it can fail in a worse way. So here you could have extra polynomials that do not vanish, that do not tropically vanish on the variety. Yeah. In this particular case, in this example, I'm not sure if there are more polynomials. That's a good question. I'm not sure. I would say I would have to think about it, but yeah, in general, it's definitely not the case. And tropically, that can.
The classical ideal is radical in this case.
Yes. Yeah. So I need to think about it, but I would say in general, it doesn't happen, and there is no well-defined notion of a radical tropical ideal. That's what you. So let me continue and tell you that this area of algebraic foundations of tropical geometry. Well, the idea is that so far a lot of the developments in tropical geometry have focused on studying the varieties, the tropical varieties. So these polyhedral complexes that you get when you tropicalize classical varieties. So you study them as geometric objects and you do geometry of them. But when we do classical algebraic geometry, we have two sides of the story. We have the geometric side, but equally important, or perhaps even more important later, is the algebraic side. You have a correspondence between varieties and radical ideals, or schemes and ideals, if you're thinking of affine space. And we would like to develop some theory like that for tropical geometry. We'd like to have some kind of tropical algebra that we can move, that we can use to move between the geometry and the algebra back and forth. For instance, a phenomenon that is inherently tropical is that there are some tropical varieties that you can decompose into irreducible varieties in different ways. So there is not a unique irreducible decomposition of tropical varieties. Here's one example of that.
Is the problem that the map trop that constructs a tropical polynomial from an algebraic polynomial is not really well defined?
No, the map that constructs a tropical polynomial from a classical polynomial is well defined. So once you write your polynomial as in a non-redundant way, as just a sum of monomials together with their coefficient, and you don't repeat monomials, then the map that tropicalizes that polynomial is well defined. You just change the coefficients by the valuations.
Oh, I think the question here is pointing at an example that the polynomial 0 and the polynomial x minus x seem to give different tropical polynomials. Right.
Yeah, so yeah, that's a good point. But when we define this tropicalization, we would not accept the second expression that you have there. X minus x is not really the expression of a polynomial because you have a repeated monomial there. So this procedure that I was describing for tropicalizing a polynomial, you first write your polynomial in a reduced way, you don't repeat any terms, and then you tropicalize. And that's a well-defined operation. But in your example, it's hidden the fact that, yeah, that in classically you have cancellation sometimes. X minus x can cancel and give you 0. And that's exactly what creates problems when you tropicalize, yes. But the procedure for tropicalizing a classical polynomial is well defined. Okay, so I was talking about this example. Here's a tropical variety, the union of these three lines, for instance. You can see it, you can decompose it as a union of two tropical varieties in different ways. I'll talk about non-realizable varieties when I get to that, but so you can decompose it as the union of a line, a tropical line, and a tropical quadric. That will give you this variety that we started with, or you can decompose it as a union of these three lines, horizontal, vertical, and diagonal, and those are also tropical varieties, and that would give you a different decomposition of the variety into irreducible to varieties that you cannot further decompose. It would be nice to have a theory, an algebraic theory of tropical geometry, that if I give you this object, not as a geometric object, but if I give you as an algebraic object, then you would be able to distinguish if you were, in the case, line together with a quadric, or maybe union of three lines. So these algebraic foundations would allow us to deal with these two cases differently, to make a difference between, to distinguish between these two cases. So in general, what I'm saying is that we would like to develop a more general theory of tropical schemes, not only tropical varieties, in which a variety, we can not only think as a geometric object, but maybe as a collection of tropical polynomials or something. We don't want to think of it as just a collection of points, but maybe we want to think about it as a collection of the functions that vanish on this variety. And and maybe try to generalize things to this level of schemes if you have read or seen schemes before. We would also like to have tropical machinery, like purely tropical machinery, to study tropical geometry. So far, the way we've defined tropical varieties by tropicalizing classical varieties, we always start with a classical variety, tropicalize it, and that's how we get a tropical object. But we always start with some classical variety or some classical ideal. It would be nice to have some machinery, some algebraic tools that were purely tropical, and we could talk about tropical varieties and tropical ideals without having to always make reference to some classical object that we start with. Okay, so that's also another hope that these algebraic foundations try to fix. And we would also like to include non-realizable tropical varieties in our study. So what is this? Well, remember that the first week we saw this theorem that told you that every tropical variety, the tropicalization of a classical variety, was a polyhedral complex, but it was a very special polyhedral complex. It was pure dimensional. For instance, if the variety you started with was irreducible, it had pure dimensions, it was connected in codimension 1, and it was balanced. If you look at any face, face of codimension 1, if you look around it, you see this zero tension condition around it all the time. So it turns out that there are polyhedral complexes that satisfy all those properties. So you can have pure dimensional polyhedral complexes that are connected in codimension 1, and that around every codimension 1 face you see a balancing condition. But these polyhedral complexes are not the tropicalization of any classical variety. You cannot obtain a tropicalization of any classical ideal variety. So they look like a tropical variety, but they're not really tropicalization of a classical variety. So this is what I'm calling, what people call a non-realizable tropical varieties. And it would be nice to have an algebraic theory that included some of these things, if we can, that we can also maybe assign some algebraic object to these things, even though they do not come from an algebraic, from the tropicalization of a classical algebraic. So these are some hopes, some ideas for why we want algebraic foundations in tropical geometry. So this field of tropical geometry, this area started maybe in 2013 with a paper by Jeff and Noah Giansiracusa that tried to do that, tried to define what a tropical scheme should be, what kind of algebraic or tropically algebraic object we would like to associate to a variety. So maybe let me use the pen for a second here. And just remind you guys what the, let me move this to the left, what the classical situation is. So classically, sorry about the handwriting, and I don't have a proper tablet to write with, but hopefully that's readable. So classically, when you're talking about closed subschemes of affine space, what you're talking about is an ideal. So let's say you start with an ideal in the polynomial ring over a field in n variables. So this is what is going to determine a closed subscheme of affine space. Well, this determines, I guess, before Grothendieck, the way we thought about variety, the varieties defined by this ideal is this, you consider the zero locus of that ideal, and that's some geometric object, P of I, that it's a subset of the zero locus of I, the set of all points where I vanish, that vanish on I, is the variety defined by I, and it lives inside n-dimensional affine space, or n-dimensional Euclidean space, let's say. But the way you can come up with a scheme from I is you can create what is called the coordinate ring of determined by I, and what you do is you create the ring, you mod out by I. So you take the whole polynomial ring of all polynomials and you quotient by I, meaning that you identify two polynomials. So here, f, the class of the polynomial f is equal to the class of the polynomial g, if and only if their difference is in the ideal. And you can think of this coordinate ring as the ring of polynomial functions on your variety, on this set. That's intuitively what one is trying to do here. So you want to say that the two polynomials are equal, f and g are the same polynomial in the variety V. Well, if their difference vanishes, is an element of I, meaning that it vanishes on the variety V.
So Felipe, we have another question. Going back a few slides, is it even possible to find a principal tropical ideal? Does that concept have any meaning for tropical ideals?
Yes, that's a good question. So I still haven't defined what a tropical ideal is, but it is true that the great majority of them are not going to be principal, and maybe the only principal ones are like monomial tropical ideal. So yes, it is the case that a tropical ideal is almost never going to be principal. So that's not a very useful notion for tropical ideals. Yes. So the way you come up with a scheme from an ideal I is you want to create this coordinate ring where you identify two polynomials if their difference is in I, meaning that their difference vanishes on the zero locus of I. That's what you do classically. Now you want to do the same thing tropically, but the problem is that here we have a negative sign. Here we're saying f minus g is in I, and remember that tropically we don't have this minus sign. So we need to do something different. And what happens is that, well, classically it is enough to record which functions vanish on your variety. That determines already when two functions agree on the variety by this trick. Two functions agree on the variety if and only if their difference vanishes on I. But tropically, you're not going to be able to do this. What you're going to do is you want to record all the fibers. So you want to record all the possible f is the same as g in your variety g. You cannot only record the ones that are equal to 0. So that leads to the concept of a congruence. What you want to do tropically is to use this notion of congruence on the tropical polynomial semiring. So that's what Jeff and Noah Siracusa did in 2013. They thought about, well, we need a congruence. What is a congruence? It's simply an equivalence relation. Remember, we just want to say when two polynomials, tropical polynomials, are the same in your variety. That's the intuition we should have. So it's an equivalence relation that satisfies this property. If f1 is the same as g1 and f2 is the same as g2, these are tropical polynomials, Then the sum of F1 and F2 should be the sum of G1 and G2. And the product of F1 and F2 should be the same as the product of G1 and G2. Okay? So, yeah. So these are, if you're thinking that you want to say when two tropical polynomials are the same on your variety, these are definitely natural conditions you want to impose on your equivalence relation. If F1 is the same as G1 on your variety and F2 is the same as G2 on your variety, then the sum should be the same as the sum and the product should be the same as the product. And maybe I should say, let me write it down here, that if you take this equivalence relation, if it is a congruence, then you can create the quotient. If you take the semiring of tropical polynomials and you identify polynomials that are equivalent, so you take the equivalence classes of this equivalence relation, that they can be given the structure of a semiring. And that's because precisely these properties makes addition and multiplication to be well-defined. So this is a well-defined semiring. Okay, you define the multiplication, the addition of two equivalence classes, you can define them by representatives, and it's well-defined because of this property, and the multiplication you define by representatives, and it's well-defined because of that property. So congruences are exactly the equivalence relations that allow you to define a quotient semiring in this way. And you want to create one such congruence given a classical ideal. So on the tropicalization of a classical ideal that tells you when two tropical functions are the same on the tropicalization of this variety. So that's what they did. They named this congruence the bend congruence. So let me tell you what that is. First of all, if you take a tropical polynomial, let me write it like this. So a tropical sum of tropical monomials, each one of them with a coefficient. And V is in the support of F. So maybe let me write what the support of F is. The support of F is just the collection of, maybe let me write it here. The collection of monomials, I guess, of exponents here. Such that the coefficient of that monomial is not infinity. So the monomial actually appears in your polynomial. That's what I'm calling the support of a polynomial. Just the set of monomials that you see, or the exponents of the monomials that you see in your polynomial. Then I'm going to denote by F lower V hat. Just take the same polynomial, but remove the monomial that corresponded to V. So if you have a big polynomial, that's F, and F sub V is just the same polynomial, but delete one of the monomials that you see. Delete the monomial V. What is the bend relations associated to a tropical polynomial? F is declaring that F is equivalent to F removing each of its monomials. Okay, so if you have X plus Y plus 0, the bend relations associated to X plus Y plus 0 is declaring that X plus Y plus 0 is the same as just Y plus 0 when you remove X, X plus 0 when you remove Y, or X plus Y when you remove 0. So each polynomial has a collection of bend relations associated to it. And then the bend congruence is the equivalence relation that you get closed under addition and multiplication that you get when you that is generated by the bend relations of all the polynomials in your tropicalization of J, or the tropical polynomials in the tropicalization of J. So, yeah. So this is some congruence. And you want to think of, let's do the X plus Y plus 0 example. So if you have, right here, if you have this tropical polynomial, X plus Y plus 0, you know that this describes the tropical variety given by the line, the tropical line. So this is the tropical vanishing locus of X plus Y plus 0. And in this variety, you note that this tropical polynomial is the same than just X plus Y. Why is that? Well, because on this variety is exactly the set of points where the minimum is attained twice. The minimum between X, Y, and 0 is attained twice. So that minimum is the same as if we remove 0, that minimum has still to be the same on this line because it was attained twice. So if it was 0, if it was actually 0, I can remove it because it has to appear in one of these two as well. And it's also the same as y plus 0, again, because the minimum was attained twice between these three, and it's also the same as x plus 1. So these bend relations are natural relations that hold between tropical polynomials when you restrict them to the variety that you're looking at. And that's the algebraic object we want to associate to the tropical variety. So the coordinate semiring, you should think of this as the tropical polynomials restricted to your tropical variety, a collection of polynomials without addition and multiplication. You're going to define as this quotient semiring, the semiring of tropical polynomials, where you identify polynomials according to your bend relations.
Oh, you don't keep removing monomials?
Well, you do that for every monomial that appears in your polynomial. Here I'm just taking one polynomial and it has 3 monomials. And I'm removing, so I'm declaring that polynomial to be the same as removing the last one or the first one or the middle one. You do that for every monomial that you see in your polynomial. So I'm not sure if you mean, here I removed the 3 of them, 3 monomials, and these are the 3 equalities that you get from removing those. But you need to do that for all the polynomials in your ideal.
So is the equivalence relation generated by the bend relations a congruence, or do we look at the congruence generated by the bend relations?
Is the equivalence relation generated by the bend relations a congruence, or do we look at the congruence generated by the bend? We look at the congruence generated by the bend relation, yes. So in general, you're going to need to close this under addition, under multiplication, but also under transitive closure so that you get an equivalence relation. Yeah, so you do need to close it under all these things so that you get actually a congruence, an equivalence relation satisfying this property. Yes. Okay, so this is the object Jeff and Noah Giansiracusa proposed in 2013 that we should associate to a tropical variety, an algebraic object that encodes, yeah, that we should deal as the scheme associated to the ideal J. Anna is asking, what do you mean by the set of equivalence relation in the definition of bend F? Yes, so what I mean is, this is not only one relation, but it's a bunch of relations, one of them for each monomial that you see in your polynomial. So for example, here, this example that I did here, this is the bend of x plus y plus 0. Is this a collection of it's going to be a collection of equivalences. It's declaring that this polynomial is the same as this polynomial, but also the same as this one and the same as that one. And then the bend congruence is taking all these relations that you have from your polynomials and then just creating the congruence that they generate. Bend F is not a set of tropical polynomials, you're right. Bend F is a set of equivalences. So you can think of it as a subset of a collection of pairs of polynomials. Each one, like this one equivalent to that one, this one equivalent to that one, and so on. It's not just a collection of polynomials, it's a collection of equivalences, or yeah.
So do you also get x plus y equals x equals y, for example, or you only remove one monomial?
You only remove one monomial, good question. So you only remove monomials in your original polynomial f. You don't remove, oh yeah, that's the question someone was asking before. Yes, you only remove one monomial every time. You don't remove 2 monomials. And that makes sense if you think about it, because, so think about the tropical polynomial, just x. This tropical polynomial is definitely not the same as these ones on all of these tropical variety. So if you are on the ray where the minimum, where y is equal to 0 and x is larger, y is equal to 0 and x is larger, this one, here the tropical polynomial x has different values than these ones. Yeah, so you're only allowed to remove one monomial from the original polynomial, and that still preserves the minimum, because you know that the minimum is attained twice. But if you remove 2, the 2 that you remove could be the ones achieving the minimum, and then you get a different polynomial.
And there seems to be a typo appearing. I can't see it yet, but it says that x plus y appears twice and x plus 0 does not appear.
X plus y appears twice, but x plus 0 doesn't. Oh, yes. Yeah, thanks very much. So the last one I wrote, this is too big. Yeah, this last one should be x plus 0. Thanks.
The next question is, why is this a good choice? Is there any intuition for this?
That's a very good question as well. And I mean, the intuition is the intuition I've been trying to give you here, that you want to declare when two polynomials are the same on your tropical variety. And all you know is that the tropical variety is defined by a collection of polynomials where the minimum is attained twice. So based on that, you can say, yeah, we know that these polynomials have to be the same on that variety because the minimum between these three monomials is attained twice on this line. But more than that, I think a motivation for why this is a good choice comes later when we start developing the theory and realizing that, okay, this satisfies a lot of nice properties and we can do lots of nice things with this. But so far, I think the intuition for why this is a nice definition is just sort of trying to make an analogy to the classical case.
By looking at the bend of f, are we kind of breaking the tropical line, like seeing the irreducible pieces?
Yeah, good question. I wouldn't say that. I would say that, I would say just, I mean, the tropical line is already irreducible as a tropical variety. And what the monomials correspond to the yeah, I would say that no, maybe the better intuition to have is that we want to declare when tropical polynomials are the same on a variety, and that allows us to remove one monomial, but maybe not a decomposition of the variety into smaller pieces. Okay, so that's the idea that got this area of tropical geometry started. We should associate some kind of semiring to a tropical variety, and that should be the algebraic object that we deal with. So let me continue. What are nice properties? What are nice nice things about this coordinate semiring? Well, for example, this semiring determines the tropical variety. The tropical variety trop v of j, the tropicalization of your variety, in a very simple way. I mean, very in analogy to what you have in the classical case. If you just take the collection of homomorphisms from your coordinate semiring into the tropical numbers, so these are semiring homomorphisms, that is in bijection with the points in your variety, with the actual points. Why is this? Well, because how do you define a homomorphism from this quotient semiring into the tropical numbers? What you need to do is you need to define a homomorphism from the original big polynomial semiring, and it needs to be constant. It needs to be well behaved with respect to your congruence. So it needs to be constant on the equivalence classes of your congruence. So what that's saying is, well, you choose where to send x1, you choose where to send x2, up to where to send xn. That's giving you a point in affine space. But that point needs to satisfy the bend relations, meaning that the value that you assign to x plus y plus 0, in our example, should be the same as the value that you assign to x plus y, and it should be the same as the value that you apply to y, x plus 0, and same as y plus 0. And that's just saying that the minimum between x, y, and 0 should be attained twice. Okay? So, which is exactly the condition for that point to be in the vanishing locus of x plus y plus 0. So this equality here is just a fancy way of saying that your tropical variety is the collection of points where the minimum is attained twice for all the polynomials in trop J. But it's nice that we can recover the tropical variety from this semiring in a very natural way. And in fact, in a paper later, 1 year later, of Diane and me, we proved that you actually determine the tropical variety as a weighted fan. So remember, the tropical variety is not only a set, but it also comes with multiplicities, the multiplicities that make it a balanced fan. And you can recover the multiplicities from this semiring. If I just give you this semiring, this algebraic object, you can recover, okay, the multiplicity of this cone is equal to 3, the multiplicity of that cone is equal to 7, and so on. That's encoded in there. And later in that same paper with Diane, we proved that the bend congruence, this algebraic object that we're associating, is actually the same information as the tropical ideal that we were talking a couple of slides before. So
does this also work for non-realizable tropical ideals, I guess, or?
Yes, very good question. I still haven't told you what a non-realizable tropical ideal is, but it is true that something like this holds for congruences that do not necessarily come from a classical ideal J, but from some more special tropical ideal. Yeah, this also works, and you can recover the multiplicities as well. And this other theorem here is the same as well. Yeah, so in this paper we proved that the bend congruence, this semiring, is exactly the same information as the tropical ideal. So the tropical ideal meaning just the collection of tropical polynomials that you get from tropicalizing your classical ideal. Of course, you can recover the bend relations from the tropical ideal, and this is the procedure that we did here. You start with the tropical ideal, you create the bend congruence out of it, but you can go the other way around as well. If I give you the bend congruence, you can recover the tropical ideals in the tropical polynomials in your tropical ideal just by, well, it's the collection of polynomials such that the bend relations of that polynomial are inside the bend congruence. So the bend congruence is defined as the congruence generated by the bend relations of all these polynomials. And it turns out that you don't include any more bend relations of polynomials other than those. So if you just look at which polynomials have their bend relations included in this congruence, you recover the original polynomials you used to define it. So question, if you have the correct type of weighted fund, can you construct a tropical ideal? That's a great question as well. And so far we don't have, you would want to say is the collection of polynomials that vanish on this tropical variety or something like that. I don't think we know how to do that so far. Yeah, we don't know how to start with a variety and construct an ideal, an algebraic object out of it, not in general. I'm describing how to do it in the realizable case, but in more general, we don't know how to do it. Okay, so the moral of this slide is that the scheme structure that you want to associate to a tropical variety is given by either the bend congruence associated to it, or by the tropical ideal, meaning the collection of all tropicalizations of the polynomials that define the classical ideal, that are in the classical ideal. That's the algebraic information we want to deal with. Okay, I'm running a bit out of time, but let me start speeding up now. Well, that means that we're definitely interested in tropical ideals, meaning ideals in the polynomial semiring of tropical polynomials. Okay? We want to look at ideals. So far, we've only been looking at the ones that are tropicalizations of classical ideals. But maybe if we want a general theory that doesn't involve always having a classical ideal, maybe we want to just think of general ideals, like all possible ideals in this tropical semiring. It turns out that that's not a very good idea because there's many problems. So one simple problem but important is that multiplication in this tropical semiring is not cancellative, for instance. Here is an example of it. If you take this quadratic polynomial and you multiply it by this other quadratic polynomial, you get this quartic polynomial. That's the same as just taking the first one squared. Okay, so that means here you have an equality, but you cannot cancel the x squared plus x plus 0. So multiplication is not cancellative. Another much more serious problem is that the tropical polynomial semiring is not Noetherian. Ideals are infinitely generated. We just saw an example in the first slide, for instance, in the second slide. Here's another example. If you take the tropicalization of this classical ideal, x minus y, well, you get x plus y, but for example, in the classical ideal, you have x squared minus y squared, and that tropicalizes to x squared plus y squared. Or you have x cubed minus y cubed, and that tropicalizes to x cubed plus y cubed, and so on. Classically, you only need this polynomial to generate all of them, but tropically, you don't. So a similar phenomenon to the one we were discussing at the beginning is x squared plus y squared is not a multiple of x plus y. there is no way of canceling the xy term when you multiply this by a linear polynomial. And same x cubed plus y cubed is not a multiple of any of these two. It's not a polynomial combination of these two. So you need to add it as a generator and so on. You always need more and more generators. So you end up with an infinite generated ideal. Most importantly, is that varieties of arbitrary ideals can be fairly arbitrary. So what do I mean by the variety of a general ideal? Just do the same thing we've been doing so far. For a polynomial, you can define the hypersurface associated with that polynomial as the set of points where the minimum is obtained twice. And for an ideal, just take all those conditions for all the polynomials in your ideal. Well, it turns out that if you have a general ideal in the polynomial semiring, then the variety might not be polyhedral, for instance. It's not that it doesn't look like a tropical variety, it's that it might be a completely non-polyhedral object, like an oval, like some weird shape, something non-polyhedral.
Yeah, question again, do these problems come from a distinction between polynomials and polynomial functions? Which of the problems vanish when talking about polynomial functions?
I would say it doesn't come from that. So in fact, when you're looking at the varieties, for instance, here you only care about the polynomials as functions and not as so this problem, for instance, still persists if you think of polynomials as functions and not as polynomials. This one also persists because all these functions are different. So I would say most of this, even this multiplication not being cancellative persists. So here it is true that these two polynomials are the same as functions, but even if you restrict to functions, you can get examples where multiplication is not cancellative. So I would say all of these polynomials problems persist. It's not a problem of dealing with functions instead of polynomials. Yeah. But definitely, I think that's an interesting question that perhaps one should think more carefully about. And maybe there's more to say about what you can recover, what you can get when you restrict to functions. Yeah. One last example of things that can go bad if you consider general ideals is that the Nullstellensatz is not true anymore. There are ideals, whose variety is empty, like this one, x plus 1 and x plus 2, the ideal generated by those two tropical polynomials. This first polynomial is requiring that x is equal to 1. Minimum attained twice between x and 1 means that x has to be equal to 1. This one is requiring that x is equal to 2, so the variety is empty. But the ideal is not the full ideal, the full polynomial semiring. So it's a proper ideal with an empty variety. And classically, that doesn't happen. That's what the Nullstellensatz says. Tropically, it can happen. Yeah. Why is this ideal not the full polynomial semiring? Because any possible multiple of these two guys is going to have the x there. Remember, you cannot have cancellation here. So any polynomial combination of these two always has some x somewhere. Classically, you could take the difference of these two or something and cancel out the x, but tropically, you cannot do that. So these are problems that happen.
Is the tropicalization of the ideal generated by x minus y finitely generated if the valuation is non-trivial?
Good question again, no. So this doesn't have to do with evaluation. The evaluation would just change some of the coefficients that you see here, but this is always infinitely generated. Yeah, it's not a problem also of the valuation. So what we want to do now is try to fix these problems. And the way we're going to fix it is by, let's not look at all ideals of the tropical polynomial semiring. Let's just consider a smaller class of ideals that looks more like the ones that we know are well behaved, the ones that are tropicalizations of classical ideals. And maybe this is almost my last slide. But this is the key slide. This is the one with the definition. Well, let's think about what tropicalizations of classical ideals. Why are they well behaved? What special property those tropical ideals have? Well, it turns out that if you start with a classical ideal, then fix some degree d greater than or equal to 0. If you consider the set of polynomials in that ideal of degree at most d, that's a linear subspace. So yeah, truncate your ideal at some degree. Consider all the polynomials of at most degree 7. That's a linear subspace because you can add those polynomials and you will get a polynomial there. you can multiply them by scalars and you get a polynomial there. You can subtract them and you get a polynomial there. So that's you get a linear subspace of a vector space that has dimension as many monomials there are of degree at most d. So we can identify it with k to the monomials of degree at most d. So when I write mon less than or equal to d, I mean the monomials of degree less than or equal to d. And there's going to be one dimension for each of those monomials. And you can think of that as the coefficient that records the coefficient of that monomial in the polynomial. And that means if you have if that's a linear subspace, that means that the tropicalization of these guys, when you tropicalize the polynomials of degree at most 7, that should be what we in tropical geometry call a tropical linear subspace, a tropical linear space. So that's that's the analog of a linear subspace in tropical geometry. It's some variety that behaves like a linear subspace. One way of saying what a tropical linear space is the following. So first, some notation. If you have a tropical polynomial, let's say like this, f is the sum of x to the u times some coefficients cu. When I write brackets f x sub x to the u, I mean the coefficient of this monomial in f. Okay, the coefficient of x to the u in f. What this tropicalization of J satisfies is that it satisfies this monomial elimination axiom. So let me say what I've written down here. Whenever you take a monomial, so let's say you take two polynomials f and g in your tropical ideal J, in trop of J. If you have some monomial where they have the same coefficient, the coefficient of f is the same as the coefficient of g in that monomial, in the x to the u monomial, and it's not infinity, then there is, because these polynomials come from tropicalizations of classical polynomials, if you take the classical polynomials, there is some way of like subtracting one from the other to make that monomial vanish, right? So what that means is that in the tropicalization of your ideal, there needs to exist an h where that coefficient, the coefficient of that monomial, is infinity, and the coefficient in all the other monomials only increases. And that's, remember, because the coefficients are the valuations of the classical coefficient. The tropical coefficients are the valuations of the classical coefficient. So when you take differences, the valuation can only increase. And actually, this is an equality if the two valuations were different, if the two coefficients were different. Then when you take the difference, the valuation has to take the minimum. What is I? What is I?
I don't see it either.
Yes, here I wrote I. Thanks. This means this is trop J. I is the tropicalization of J. So yeah, I'm missing something here, which is that f and g should be polynomials in the tropicalization of J. If there is a monomial where they have the same coefficient, then there is another polynomial h in the tropicalization of J, such that the coefficient of that monomial is infinity, and the other coefficients are at least the minimum of the two with equality when they are equal. Okay.
Same degree requirement?
Not necessarily with the same degree. You could, you don't need to require that they have the same degree. All you want to say is that, I mean, if you take one of degree 7 and one of degree 5, they both live in the subspace of polynomials at most degree 7. So there is no need to require that they are the same degree. And if it's a homogeneous ideal, then you also don't need to require it, because if they don't have the same degree, then they don't have any common monomial. So we don't need to require that they have the same degree. Yeah. So this is one way of saying that the collection of the tropicalizations of the polynomials you have are a tropical linear space, are this kind of objects that we like a lot in tropical geometry. And the proposal is that that's a good class of ideals to deal with. So this is the key definition. An ideal I in the tropical polynomial semiring. Now it's not necessarily the tropicalization of anything, but it's just some ideal. We're going to declare it to be a tropical ideal if it satisfies this monomial elimination axiom. Whenever you take two polynomials there with the same coefficient in some monomial, then you can eliminate that coefficient, and there is some other tropical polynomial there where that coefficient is infinity, where that monomial doesn't exist, and the others are only go up. If you have heard about tropical linear spaces, that's this condition is exactly that condition of being a tropical linear space. So I is a tropical ideal if and only if for any degree d that you choose. If you truncate your ideal at degree d, if you consider all the tropical polynomials of degree at most d, that's a tropical linear space in this R bar to the monomials of degree d. And if you like matrix, this is very related to matrix. Tropical linear spaces are very related to matrix. For instance, if you only deal with the trivial valuation case, in which the valuation is either 0 or infinity, then you can say that a tropical ideal is an ideal in which the polynomials of degree at most d are the vectors of a matrix, like this, the unions of circuits of a matrix. Unfortunately, I don't have time to tell you more about this very nice connection to matrix, but if you've heard that before, then that's what's going on behind this. So let me go to my last slide, which is examples to understand what this is about. This ideal, the ideal in the tropical semiring generated by just one tropical polynomial, x plus y, is it a tropical ideal? Does it satisfy this monomial elimination axiom? We kind of discussed this already. The answer is no. So what's the problem here? In degree 1, you have only scalar multiples of this polynomial, that's fine. But in degree 2, you're gonna have x times this polynomial, so x squared plus xy. And you're gonna have y times this polynomial, which is xy plus y squared. That means that you have two polynomials, maybe two polynomials in your ideal, this one and this one. They have a common monomial with the same coefficient. xy appears with coefficient 0 here, with coefficient 0 here. So there should be some other polynomial in your ideal where this monomial doesn't exist, and it uses the monomials that remain from these two. But that's, so you would have to have x squared plus y squared, but that's not in this ideal, as we said. X squared plus y squared tropically is not a multiple of x plus y. So that's why this one is not a tropical ideal.
If the coefficient is infinity, then it is omitted in the notation.
Yes, so you don't have to write it. I think the way I wrote the axiom, I would allow some of the CUs to be infinity, but yeah, if you want to make it simpler, you don't need to write the coefficients that are infinity. What I wrote is still fine. Another example, the one hopefully I motivated you for this definition, is that all the tropical ideals, all the ideals of the form tropicalization of some classical ideal, they are tropical ideals. They satisfy this monomial elimination axiom. And they are the motivation for coming up with this notion of tropical ideal. So we want to think of the ones that are tropicalizations of classical ideals. We want to think of them as the realizable ones, the ones that actually come from some classical object. But yeah, okay, so those are the realizable ones. But this is the last point of my talk, is that there are, in general, most tropical ideals, most ideals that satisfy this monomial elimination axiom, they are not tropicalizations of classical ideals. They are not realizable. In the coursework, in the exercises tomorrow, you'll see there's one example of one of them, of one tropical ideal, one ideal that satisfies the monomial elimination axiom that doesn't come from the tropicalization of a classical ideal, that is not realizable. And this is a little bit tricky because in order to define the ideal itself, it needs to be some kind of combinatorial construction that I need to convince you that the polynomials I'm giving you satisfy the monomial elimination axiom. So usually that involves some tricky combinatorics. And but yeah, maybe I won't say more than that today. But there are lots of non-realizable tropical ideals, and in fact we expect that that's the norm. Tomorrow you'll see one that is generated by polynomials that look like this, very geometric combinatorial notion. So that was my talk for today. The idea now is that in 10 minutes we have a mini exercise session to practice all these notions. Tomorrow there's a problem session 1 where you have some problems to practice all these things. Wednesday, there's lecture 2. It's going to be about properties of tropical ideals. So far, I've only told you the definition, but they have many nice properties, and there's lots of things you can do with them. And Thursday, there is the problem session number 2. So thank you very much.
Let's thank Felipe for his talk. And once all the claps are over, we have also time for questions. And one question was already there.
Yeah.
So tropically, I think you want to read this yourself as well, but it's x plus y times x plus y is equal to x squared plus xy plus y squared plus x squared plus y squared as polynomial functions. Can we say that the tropicalization of x minus y is generated by x plus y if we regard polynomials as polynomial functions? Can we simplify things this way?
Yes, so it is true that I agree that if we think of polynomials as functions, then that ideal tropicalization of x minus y would be principal. But the main issue is that we don't want to think of polynomials as functions, right? The moment we think of polynomials as just functions, we're losing the algebra and we're just thinking about the geometry. If we just care about how these functions act on the plane, like what value they have on the affine, on the points, then really we're ignoring the algebra behind this. We're identifying lots of things that we want to consider as different. We're just thinking of them as the same object. And that's exactly what we don't want to do. We want to have different algebraic objects that we can associate to the same variety. We want to have different schemes that we can associate to the same geometric object. And if we think only of polynomials as functions, I think we're not going to be able to do that. So yeah, some problems would be fixed, I agree, maybe in some examples, but in general, I don't think we want to do that. Yeah, very, very good point.
Is a tropical ideal realizable if and only if all the associated matroids are realizable?
Also, excellent question. The answer is no. It is possible that all the matrices that you have, all the tropical linear spaces you have are realizable. In fact, I think the example I have in the problem set is like that. All the matrices I give you are realizable matrices, but when you think of all of them together forming a tropical ideal, it turns out it's not realizable. So it's not a property of each of the degrees, it's a global property of the whole ideal, the realizability.
Are there more questions? Next question. If I am primarily interested in studying classical varieties by tropical methods, is there a nice example where non-realizable tropical varieties should appear?
I would say yes. Don't have a concrete example in mind, but for example, if you want to study tropical linear spaces, when you're doing tropical geometry, a lot of things that you do classically, you need to use linear subspaces. And that means that in tropical geometry, you're going to have to deal a lot with tropical linear spaces. When you try to understand what tropicalizations of classical linear subspaces are, you're led to this notion of tropical linear space. And as soon as you try to understand them, you'll realize that they satisfy properties, they correspond to matrices, basically. And there's lots of non-realizable matrices. So you're immediately into this realm where you have a lot of non-realizable things that do not come from tropicalizing something classical. But if you want to understand the tropicalizations of the ones that do come from classical things, you're going to have to understand the theory of these non-realizable ones as well, because the combinatorial properties are the same. So you have to do matrix theory even for non-realizable matrices, and understanding that helps you understand the ones that are tropicalizations of classical things. So I think maybe you don't need to actually deal with a non-realizable variety in examples, but understanding the general behavior of the non-realizable ones, that includes understanding the behavior of the realizable ones. And I think that's where the value is.